Hello everyone, I'm Zijie Huang from Peking University. The title of my speech today is An Efficient QP Variable Convolutional Neural Network Based in Loop Filter for Intra Coding. My speech consists of three parts: introduction, proposed method, results, and conclusion. In-loop filtering is an essential model in video coding. On the one hand, it improves the quality of current frames by reducing the compression artifacts. On the other hand, it provides high-quality reference frames for the succeeding pictures. In the latest video coding standard VVC, there are four in-loop filtering steps, namely a Luma mapping with comma scaling (LMCS) process, followed by a deep block filtering (DBF) and sample adaptive offset filter (SAO), and an adaptive loop filter (ALF). The DBF and the ASAO are similar to that of the HEVC standard, whereas LMCS and ALF are newly introduced in VVC. Besides the built-in in-loop filters in video coding, various convolutional neural networks-based CNN-based in-loop filters have been proposed in recent years. Zhang et al. Proposed a very deep recursive residual CNN RRCNN to recover the reconstructed Intra frame, and Zhang et al. Introduced a deep residual high VCN RHCNN based in filtering for both intra and inter mode in HEVC. More recently, Wang et al. Designed a dense residual CNN based in filter DRNLF for VVC. Here we present one popular architecture used by many CNN-based in-loop filters. Typically, since the compression noise levels are distinct for videos compressed with different quantization parameters (QP), currently there are three ways to make models to be adapted to different QPs. Some methods use one model for each QP. In this way, we need train too many CNN models for the whole QPs. To address this issue, Zhang et al. Merged the QPs into several bands and trained the optimal model for each band, but they still had to train and deploy several networks. Song et al. Proposed a QP map method so that only one model needs to be trained. They combine QPs as an input and feed them into the CNN training state by simply feeding the scalar QP into a matrix with the same size of input frame and or page. However, these QP combined models are inferior to the QP separate or QP band CNN models in terms of RD performances, and their scalability are also not strong. So inspired by kernel attention model, we propose a novel QP attention model to avoid training and deploying multiple networks. The overview of the proposed QP attention model is introduced in the future. Giving a future map F as input, QP attention model infers a 1D QP attention map M. Then the attention values are broadcast along the kernel dimension and product with the input features and output the refined features. The process of generating the QP attention map is as follows. Giving a QP value Q in the omega. Since Q is an entangled value, we first map Q to a vector V by one encoding. Then QP attention map M is calculated by the formula. For the process, we can see that the QP attention map assigns different weights to each kernel of the input future map according to the QP value. So the model can capture compression noise level along different QPs. Meanwhile, the model can also imply meaningful features along kernel dimension through this process. Moreover, compared with other methods, the proposed QP attention map has stronger scalability, which can also be easily applied to other discrete variables. For example, QP, for example, frame types. Our proposed QP attention model can be implemented in any learner. To better utilize the QP information, we implement the QP attention model in the rational block, and we also propose a rational feature aggregation model to make a better use of the local rational features. It contains three rational blocks and one convolution learner. The input is extracted by three rational blocks at three different levels. Then the output from three rational blocks are contacted, and a 1 times 1 convolution is applied at the end of the model for kernel dimension reduction. Then we design to train this model. We mix the training data with 4 QP, 22, 27, 33, and 37 together and train the model. Then we plot the valid image cumulative proportion over the PSNR gain rate for different QPs. The L init is the mean square error between input and the ground truth. The LIC is mean square error of output of the network and the ground truth. From the curve, we can find the network has lower PSNR gain rate overall on the dataset with smaller QP, especially at QP is 22. Obviously, smaller QP means less compression artifacts, and we don't expect the network to pay much attention on data with less compression artifacts. 2. The PSNR gain rate of 80% of the varied data is less than 10%. That is, the varied data with low PSNR gain rate accounts for a large proportion. So we expect the network to focus more on data that had low PSNR gain rate. Then we design the focal MSE to train a more robust model, where the RQ is a weighting factor over QP value, and the gamma is the focusing parameters. As for training detail, the bench size is 64, and we train the model for 50 aspects. The initial learning rate is 10 to the power of -4, and fine-tuned with 10 to the power of -5. The proposed method is implemented as an additional tool of in-loop filters between DBF and SAO, and incorporated into the VVC reference software VTM6. The coding efficiency is evaluated on the standard video sequence from class A1 to class E, recommended by JVT. We use the Intra configuration suggested by VVC common test condition. The anchor for all experiments is VTM6 with all built-in in-loop filters enabled. First, We compare our QPALF with VTM baseline and two CNN-based in-loop filters, RHCN and DRALF, for for fair comparison. We also train the model, use our dataset, and integrate the chain model into VTM SIG between DBF and SO. The results are displayed in the table. It can be seen obviously. Our QPAF further improves the coding efficiency, which obtained 4.03% base bitrate saving overall for Luma kernel on all the test sequence. To further verify the efficiency of the proposed model, we also compare our QPAF with QPMLF and QPAF-S. The QPAF-S is the QPAF model chain severity on 4 QPs. The QPMLF is the QPAF without QP attention model, and use QPMap method. As we can see, compared with QP separate model QPAFS, the performances of the QP combined model QPMLF decrease, while our model achieves even better coding performances. We also depicted the PSR gain of three models on multi-QPs. We can observe that our QP attention model obtained the highest QP PSR gain over all QPs, which also demonstrates the generation ability of the proposed method. This figure illustrates the subjective with quality comparison among four approaches. It can be observed that the image enhanced by our approach remain less distortion than those by other approach. For example, the clear edge of the basketball net line. We also display the raster map of three methods over VTM baseline. Compared with RHCN and DRNF, our method can restore more image texture detail. The table shows the average encoding or decoding time increase and the parameters of different models. All of the networks are conducted with GPU acceleration. Our proposed QPAF has less model parameters overall than IHCN and DRN. Compared with QPMF, our model achieves much better RD performances with little complexity increase. Overall, in this paper, we propose an efficient QP attention model, and we design a QP network architecture that is equipped with controllability for different QPs. And we introduce a focal MSE to train a more robust model. In the future work, we will optimize our QP attention model and extend our model to intermode. Thank you. If you have any question, please send